Okay, we are recording. So basically, a couple of things. We have the exam on Saturday, where we post it automatically online at noon, and it's due Sunday at noon as well. So you got 24 hours to complete it. It consists of three problems. Say one of them are extremely simple, and the other two are a bit more tricky. It took me approximately like an hour to complete, so it should take you guys maybe at most an hour as well. I don't think it's going to take you much longer, but you get at 24, so it should be more than plenty of time to do it. A couple of things, hand in your assignment as a PDF. I'll make an announcement as well. It's easier for me to make sure there's no issues, and double check what you hand in. So check if you scan it. You can use a phone app. You can just make a picture and convert it to a PDF. There are a bunch of apps that do it for you. So, but double check before you submit it that it's actually readable. I advise you using a pen instead of a pencil. It's just more readable. And start every problem on a new page as well. Just make it easier. Number the pages. So if I know it's 5 out of 5 or 6 out of 6, so if there's something missing and I do a quick glance, I know there's something. And also for yourself. So you make sure that you actually submit all the documents. Let me see. Yeah, I got a question from one of the students. They said like, well, I'm not exactly sure if I'm gonna keep or drop the course on. I think it's Monday's the 15th. It's the last day you can drop the course without a W or whatever it is. So if you're one of those students, just once you submit it, please note that in the email, and I will just grade you guys earlier, and I will give you a good grade as soon as I can. So some people want to drop it if they're not sure if they can continue, so I can accommodate you guys as well. With that said, today's lecture we're going to do a couple of problems, and Wednesday we're going to just continue doing problems as well. I noticed actually that I haven't posted any recommended problems, so I'll do that after this lecture as well. I'll give you a couple of recommended problems from the book on how to solve it, okay? And for today, we're going to just continue with the two problems that I posted in the lecture slides. So we can go to the correct page.
Which posting is this under? Is this under bending or stresses and strains?
How do you mean the slides?
Yes.
It's bending.
Okay.
Yeah, we're currently at bending. So we're going to continue. Let me see. Yeah, this is the problem that we stopped at last week, and we're going to just solve this problem. And there's a good example. It's not too difficult, but it requires you to figure out like 1 or 2 steps in advance, and you have to basically think about the problem before you actually can solve it. And it's a good tip to just see how you can solve this problem. And also it involves a couple of just algebra, so how to reduce the problem. So it's always good to know that. So I'm going to leave this online for you guys to on screen, and then we're going to continue on the whiteboard. So let's see. So we have a cross section, and we can immediately say a couple of things about the cross section, make a couple of observations that will benefit us. Let's draw this. This is 3A. I think this is 2A. And this is beta A. So first of all, we know it's symmetric. So IXY is equal to 0 because it's symmetric around the vertical flange. Second, let's investigate what we are given. We are given mx is equal to 15 kilonewton meter. And we are talking about sigma yield and compression and sigma yield and tension is equal to 65 megapascals. We are given that A is equal to 20 centimeters, which is 200 millimeters. Let's convert the meter to the correct dimensions, and T is equal to 1 millimeter. So let's convert this as well. So what we have here is 15 10 to the power 6 Newton millimeters. So with the given set, we can make another assumption, or observation is that there's no my given, so we can assume it's equal to 0. So with these two assumptions and the given dimensions, we can reduce the problem already, and we can look at the reduced equation that we have to deal with. So let's write out the full equation first. So we have my Ixx minus mx Ixy, Ixx Iyy minus Ixy squared, and this is multiplied by x, plus we get mx Iyy minus my Ixy Ixx Iyy Ixy squared multiplied by y. So this equation, based on our assumption, already reduces to, so we have no my given, so this drops, Ixy is equal to 0, so this drops, so this whole first term drops, this drops because both are 0, and this is 0, and this we can cancel out. So what we get is mx multiplied by y over Ixx. And the reason why you want to do this first is, now you can already see that you only are interested in the moment of inertia on Xx, and you don't have to deal with Iyy, because you don't need it. So you basically save yourself time. So let's just write this up here. So this is the equation that we need. So now we basically have to, mx is given, y is your distance to the maximum location, and Ixx your moment of inertia. So first thing that we need to do is basically determine these variables that are not given. So we have to determine what Ixx is and also what our location y is. So for Ixx, we know it's with respect to the centroidal axis. Yes.
Just going back to that cancellation. So why did we assume Iyy was 1 in this situation?
We don't assume it's 1, but it cancels out. So so if the extension of this one is mx Iyy, right? Then you have Ixx Iyy minus Ixy squared. And then here we have my Ixx, right? Oh, Ixy, sorry. Multiplied by y.
That was mx Ixx.
Let me see. So the second part of the equation I'm talking about. Yeah, the first part here, right?
Yes.
And this one was Ixx. Let me see if this is on the board. Okay. So you had an my here, and then Ixy, mx. Then let's call this delta, okay? So just save space. This is Y's equation. So here my is equal to 0, so this drops. Ixy is equal to 0, so that drops. So you get basically this is 0, so it doesn't matter what we have in the denominator, so this drops. So on the second part, we have this drops because my is equal to 0 and Ixx is equal to 0, or Xy is equal to 0. This is equal to 0. So basically this reduces to this, and now you can drop the cancels out. Okay. So what do we know about IXX? So we said it's basically around the centroid. So if this was symmetric, it would be in the middle, but we don't know what the length for beta is. So beta has basically three options. Beta can be smaller than 3a, or smaller than 3 in this case. It can be equal to 3, or it can be larger than 3. So those are the three options that we have to deal with. So and depending on this beta, so say if it was 3, then we'll be in the middle. But if it's larger than 3 or smaller than 3, then basically shifts accordingly, as either the centroid is going to be more to the bottom or more to the top. So our centroid is a function of beta, so we have to take that into account. And because we don't know beta yet, so we have to assume the worst case scenario, so it still is a function of beta, so we have to calculate what our centroidal axis is, at least for the y distance. For the x distance, we have an x symmetry, so we know what lies on that axis. So centroidal is determined by over the area multiplied by the y distance over a. And we can just start at the bottom, or you can start at the top. You just use a coordinate system as a reference, and you calculate from that perspective. So let's assume we start at the bottom. So the area is 3, by the way, everything is equal to t. So t is everywhere, it's equal. So you get 3a times t, that's the area. So in this case, if you would assume thick walled, so you get t over 2, because your centroid is slightly above it. So 3a plus, this is 2a times t, 2a times t, that's that area. And this centroid from the bottom is basically 2t plus a plus t, yeah, sorry, a plus t, yeah. And then we have the top, which is the area is equal to beta at. Beta can change, of course, and then we get t plus 2a plus t over 2. And the total sum of the areas is 3a times 2, 2a times t, 3a times t, 2a times t, and beta times t. So we get 3at plus 2at plus beta at. So we can, so if you now reduce it, say Tinwald, so we take out all the higher order terms. So Tinwald, so t equal or greater than t squared is ignored. So we can reduce this to 2a squared t plus beta a squared, 2 beta a squared t over 5 at plus beta at. So we can say at 5 plus beta. And then we can reduce this a bit easy, simplify it a bit more. So we can take at squared out of bracket, divide by at, because we have an at here. So what we get is 2 plus 2 beta over 5 plus beta a. So this is our centroidal axis. And now we have to basically take the moment of inertia with the centroid being this value. So let's do the moment of inertia. So again, 1 over 12, start with the flange, and we get basically 2a to the power of 3 multiplied by t, plus we get AD squared, because the centroid doesn't have to coincide with the centroid of this one. The centroid of the entire cross section doesn't have to coincide with the centroid of the flange. A bit more clear. In that case, we get A as AD squared. So the A part is the area part is 2AT multiplied by the D term. So D squared in this case, that will be y bar minus the centroid of this axis, the location of this axis system. So again, that's basically, we assume thin wall, so we basically just say minus A squared. And then what we see, I'm going to continue on this on the bottom, plus we basically have to take the standard term of the bottom one and the standard term of the top one. We ignore the 1/12 parts because we get a t to the power of 3, so we ignore that part, okay? So the standard part of the bottom is 3AT, that's the area. Then we have to basically multiply by d squared, and d squared will be equal to, since we took it from the bottom, whatever yc is, that's the distance to the central axis. So multiply by yc squared, y bar c squared. Similar thing we do for the top. We have the area, it's beta times at. And in this case, the distance will be, with respect to this, we're going to be 2a minus this distance, y. So we're going to get y minus 2a squared. So this will be our moment of inertia term. And then we can basically substitute the yc terms in it. So we can basically substitute 2 plus 2 beta over 5 plus beta times a, and we can do some mathematical simplifications to get a slightly nicer term out of it. So let's do that. Okay. So we get here to the power of 3 is 8, so 8/12 is 2 over 3. A to the power of 3t. Plus, basically, we get 2at, and then we get 2 plus 2 beta over 5 plus beta minus a squared plus 3at, and then we get 2 plus 2 beta 5 plus beta squared plus beta at, 2 plus 2 beta 5 plus beta minus 2a squared. And then we basically have to expand all these terms to get a solution. So I'm not going to expand anything, but you can basically say it's x minus a squared, that's equal to x squared minus 2ax plus a squared. So you can use a similar concept to it to expand this one, expand that one, and then you can basically collect all the terms. So I'm not going to give you all this intermediate steps. So I'll give you a final step. And if you take it, see, I'm missing an A here, by the way. And you can eventually simplify it to the following. You can take a cubed t out of the bracket because all of them will have an a cubed t in it. in all the terms. And what you get is 44 beta squared plus 248 beta plus 140 over 3 times 5 plus beta squared. That would be your moment of inertia. And you don't have to expect something as difficult as this on an exam, at least not an in-class exam. On a take-home, you can expect it, but then you have also more time to do it. Yes?
So before you raise, could you walk again to the sigma AY, just the numerator part,
Sigma
AY. Then you're finding the same part.
sigma. Where do you see sigma AY?
A, why with the squiggle over it?
This one?
Yes, just the numerator.
Oh, this is your what it is?
No, just explain what again. Just walk through over the 380, the whole expression.
Oh, this one. This is nothing else than Sanford calculation. So you basically do the weighted average of the areas with respect to an axis system. So in this case, we said we're going to use the weight. The central is basically nothing else than a weighted average of the areas, right? So we take this as our y reference system. So we say y starts here, goes past upwards, and we call that y bar or y tilde, doesn't matter. So what it means is, what's this area and corresponding centroidal location? So the area of this is 380, and the centroid of that corresponding location with respect to our reference axis is t over 2. Similar, what's this area is 280, and what's the centroid from this location? So if you use thick wall, so it means this is 2a, not the bottom. So this centroid axis is at A, if it was just at flange itself, but we started here at the bottom, so we have to add t to it, so we get t plus a with respect to this bottom location, right?
Why not T over 2?
Because let's, if you would say have a thick wall case, so if this was be our I-beam top, we start here. This is how we define our y-axis. Because if you say my y-axis starts here, then this one would be basically 0. Because then this t over 2 would coincide with your axis.
Again, in the last term.
And last one is, again, if you look from the top, right? So this is our central axis from the top flange. That one, the area is equal to beta AT, right? And the centroid is with this respect, this was 2a. This is t over 2. And so that must be, so yeah, this is t over 2, and with respect from this one is t. So that's where you get t plus 2a plus t over 2.
So in the first term, 3AT, T over 2, is that like assuming that the area you're taking is the, I guess, the best way I can explain it of how I'm trying to think about it is like the free floating area, so that like the center of that area is the center of that beam. So then the distance from the center of that beam to the bottom.
Yeah.
T over 2.
So to your reference axis.
Yeah.
In this case, I assume the bottom.
Okay.
It's often the best case. The best thing is when you're doing a reference. So in this case, we immediately determine that it's going to lie in the central, the x-axis. We don't have to calculate because it's metric, and then you just take the bottom. In this case, we could have said this. Okay, it's thin wall from the start, and then we said, well, the centroid of this bottom horizontal flange coincides with our location, so the distance is 0, so this one drops out immediately. We could have said that.
Okay. And what's that number in between the 44 beta squared and the 140? 240 beta?
248.
248.
248 beta. Okay, let's take a. So if you now basically plug this in, what we can do is so we can plug it into our moment of bending stress equation. So we plug in our moment of inertia, we plug in our numbers, so we basically get 15 10 to the power 6. Let's call this still y, and this what we get is 44 beta squared plus 248 plus 140, right? Over whatever we have, 3, 5 plus beta squared. And before we continue, we basically have to determine what y is. So in this case, the y is equal to the furthest distance away from your centroidal axis. But this one will depend again also on beta. If beta is larger than 3, that means your centroidal axis will be a bit higher. So the furthest distance away from your centroid will be at the bottom flange. If beta is smaller than 3, that means that your furthest distance away is on the top. So you have to basically now figure out if beta is one of these 3 conditions. And the best way to do this, and this is where this problem becomes tricky or becomes difficult, is to realize, to assume one thing. So let's reduce this a bit to basic constant. So we know mx is a fixed value. That doesn't change. Y can change, and Ixx can change. So let's call this just a number. Okay? So these 2 can change. And this is your sigma z. Sigma z is already given as 65 megapascal, so this one doesn't change either. Let's assume this just be 15 for simplicity, and this is 65. So what we can do is, we can say, let's assume beta is equal to 3. So what does this do? If beta is equal to 3, then your centroidal axis lies in the middle. Then we automatically know what y is, because that will be just a. It doesn't matter if it's on the top or on the bottom. Okay? So then we have one thing. So if I assume beta is equal to 3, and the stresses that I get, sigma z is greater than 65 megapascals, our limit, it means that our structure has failed when beta is equal to 3, right? Sorry? So if I assume beta is equal to 3, then I get a symmetrical I-beam, right? 3A, 3A, 2A, right? If I calculate my sigma, the stresses, at beta is equal to 3, and this is larger than 65 megapascals, means that I have exceeded my yield in compression and tension. So that means my structure fails. So failed structure. Okay? So if beta is equal to 3 and I fail, the only way how I can prevent this failure from happening is by basically increasing the moment of inertia, because that reduces my stresses. Because if I divide by a higher number, I get lower stresses. The only way if I can do that is by increasing beta, because this one is fixed, this one is fixed. So I have to make beta much larger in order to have a higher moment of inertia, in order to prevent the structure from failing. So we can now evaluate the stresses at beta is equal to 3 and check if this condition is met or not. If beta equal to 3 is smaller than 65, that means at 3 it doesn't fail. So that means that beta automatically is the opposite of what we just mentioned, beta is smaller than 3. And this is the, yes.
If it doesn't fail?
If it doesn't fail, it's smaller, and if it's failed, it must be larger.
So could it still be 3 if it doesn't fail? Or does it have to be smaller than 3 if it doesn't fail?
If it technically can be 3 if it doesn't fail, but that means your structure is, you want to design to get the lightest structure basically. So you basically want to be at this threshold. You would just want to hit that 65.
Okay.
If it doesn't hit 65, you basically are over designing in this case. But it technically can be 3 as well, because it doesn't fail. I think in the question we ask for find the minimum value of beta. So we basically have to be smaller. Yes.
For the sake of argument, let's say beta is equal to 3 is equal to stress is 65, so it does.
So if it's equal, then you already figured out. Then that's the minimum. So if it's equal than 65, then that's also your minimum. Because if it's either slightly more or less, means your y distance is slightly more or less, so you always fail automatically. Yeah. And if say the yield stress would be tension and compression, then you basically have you basically go for the minimum value. In this case, those two are equal the same. So if you have given a yield and compression and tension, you have the same assignment, you will go for the basically minimum to figure that out. So let's assume beta is 3, and then see if our structure fails. So if we plug in beta as 3 at IXX, so IXX beta is 3. Since we had function of beta and AT, so we can figure that out. We have A given, we have T given, so you can just calculate a given. So what we get is 4 10 to the minus. It's given in meters, so we have to go 10 million 12, 8, I'm correct? Millimeters to 12. The correct answer is, I think, is given in meters, so 4 to the power of 4. Sorry, minus 4. But it's millimeters, so you basically have to multiply by 1,000 to the 4th, so it means 1,000 times 1,000 times 1,000. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So 12 zeros, and minus 4 plus 12 is 8. Yeah, should be correct. So this is our value. We can plug this into our stress equation. We had 15 10 to the power of 6 over 4 10 to the power of 8. In this case, y is equal to, because in the center, so it's equal to A. A is 100 millimeters, so 100. So this becomes an 8. Just multiply by 100, so the 8 drops. Is 15 over 4, is 7.5 over 2, 375. Am I correct? Definitely not correct. I made a small mistake somewhere. So we have 4.
Would the centroid be A plus T? Right?
No, because we used the thin wall assumption, so you can ignore that. Stay. The correct answer should be 10. I don't know why I got 375. Let me see what I did. Made a mistake. So what's the stress again? 15 kilonewton meter. So 15 kilonewton meter is 15 10 to the power of 6 newton millimeter. That's correct. And if I have 10 to the power minus 4.
A is 200 millimeters. I guess you wrote 100 millimeters.
Oh yeah, 200. Yeah. So we get basically we get 30 divided by 4. 330. Yeah, it doesn't matter. If you plug in the numbers, you get 10 megapascals. I think that's the even more important. You get something less than 65. So at sigma is equal beta equal to 3. It's equal to say 10 megapascals for sticking with the solution manual. Is equal to is less than 65 megapascals. So therefore, beta is less than 3. So that's how we figure out if beta is larger or smaller than 3.
If we were taking this in class exam, would IXX be given, or what would be?
It
would
will
this
be probably significantly reduced in complexity.
Okay.
Yeah, but the similar solution procedure you go through. Yeah, I think this is the key aspect of this whole problem. The rest is just mathematical multiplications and manipulations. So noticing that you have 3 cases, and if you basically set it equal to 3, and if then it fails or doesn't fail, gives you the solution to beta is equal greater than 3. That's basically the most important thing from this problem. Because now we know that beta must be less than 3. That basically gives us also another insight, is that the y distance, in this case, since it must be smaller than 3, it's basically equal to 2a minus our centroidal axis. So what this means is if the centroidal axis is here, so that this automatically means since it's less than 3, our centroidal axis will be below our say midpoint. Therefore, our y distance in this equation, coordinate we just maximized, gives us the maximum stress, is towards the top. And this distance is equal to 2a minus whatever our central axis system is. Is this clear? Yeah? Okay. So we can basically plug this in, get 2a was 2a minus 2 plus 2 beta, 5 plus beta, a. And if you do it correctly, you can reduce that to 8, 5 plus beta, 8. So this is our y-axis, y distance. So we can now plug this into here and set it equal to 65, and we can solve for beta. So do it again. So we know our y distance, we know our rest of our equations. So basically what we get is sigma z is equal to 15 10 to the power of 6 multiplied by 8 over 5 plus beta, 8 divided by a cubed t, 44 beta squared plus 248 beta plus 140 over 3 plus 3 times 5 plus beta squared. Yeah. And this must be equal to 65 10 to the power of 6 megapascals. So you have one equation, one unknown. You can solve this. At the end of the day, what you can do is, you basically just solve for beta. If this was homework, I would just plug it in and then solve for beta. In this case, what you can get is actually, you can reduce it to a quadratic equation. I'll just give this if you want to do it at home, or you want to do it by hand and double check later. get this quadratic equation, and you will find that beta is equal to 2.51, and that will be your final answer. So quick summary on this problem, what makes it difficult. I think the difficult part is, in this case, realizing that your centroid is a function of beta, the moment of inertia is a function of beta, and eventually your y distance is a function of beta as well. So a couple of things, we had a couple of different y's. First at our centroidal axis that we have to figure out, which is y, and you just have to figure out, you have to realize that this y is different from this y. So, and the most difficult part is realizing that beta has the three options: smaller than 3, equal to 3, and larger than 3. And you can figure out which of the three options you have to go for by stating it equal to 3, saying it's equal, and then if this the yield stress is violated, then you know that your axis, your beta must be larger or smaller for the problem to solve. Because always assume you give a negative the minimum value of beta. Say for example, if this was given as say 5 megapascals and we got 10, right? In that case, beta would have been larger, and you solve the same thing, and you would probably create a different equation, and then you get something beta being 3.5, 3.25, something like that. Yes.
How would the y be different if our beta had to be higher?
So this is a good question. So in this case, assume if this was true, then beta had to be larger, right? So that means if beta is larger, from perspective, we just exaggerate, we get something like this. This is 3a, and this is beta larger than 3. That means our centroidal axis lies closer to the top. So yc is like this, right? Then our distance and yc is determined from the bottom. So that's how we determine. So this y would be equal, in this case, would be just equal to yc, because that was by definition we determined it from the bottom, and we are looking from this location to the bottom. So yc is equal to y. We could have determined yc not from here but from the top, and then in this case it will be 2a minus yc, and in the lower case y is equal to yc. So this will be for beta less than 3 and beta larger than 3. So again, you're free to choose your coordinate system, or how you determine the centroidal axis, as long as you stick with that, and you realize that the rest of the equations has to follow suit.
So the 2m minus yc is only applicable if it's a thin walled structure, I'm guessing. Because if there's a significant thickness, you have
Yeah, because then you have to, here it will be 2a plus t. Yep. Okay. I think the next problem, I will go through that one slightly faster. 20 minutes for that one. Let's see if we go to our lecture slides again. So there was this problem. Let's focus on the second problem. So we figured out that beta is equal to 2.51. So this is actually a good problem to think about, because the solution requires you one step ahead, and it's not so obvious. So he says you have two cross sections, square and I-beam, both of them in the same moment around the x-axis. Another thing, this double lines, it basically means moments acting around that axis. So the double lines in the x-axis means the moments acting around that x-axis, and it also means that the moment follows the right-hand rule. So basically means point your finger in the direction, if the axis, the two arrows point in the same direction as your positive x-axis, means that moment is positive. If they point in the other direction, then it's negative. Because we will use that double arrows to indicate moments.
So, in these cases, the top surface is going to be in tension, and the bottom surface is.
So look at this, yeah. So we as an engineer, we have to decide on this following structure. We have to select the best structure, which is which is the best. And I will get to that wording later. So we can choose from a moment from a square and an I-beam. And you have also given Poisson ratio and what is that, John's modulus. And there's something I'll often do is sometimes you have given more information that you actually need. You don't have to be worried about it. If you haven't used, say, a variable in the problem, it's often you just given more information. So don't be spooked by it. So let's do this problem. So again, I'll go through it a bit quicker. Symmetry, xy is equal to 0. My is equal to 0 since it's not given. So our equation reduces immediately to moment around the x-axis times y over ixx. So moment is given, y is basically symmetric. So in this case, it will equal to a over 2. So let's calculate the moment of inertia of the two different cross sections. So the square. So we get 2 times 1 over 12 a cubed t plus at a squared. So times a squared. A bit more correct. So basically, this is the vertical flange, the two vertical flanges, and these are the two standard terms from the bottom and the top flange, because the thin weld, the 1 over 12 part drops out. Good. We can do the same thing for the I-beam. And in this case, we get 1 over 12 a cubed t plus 2 times at times a squared. So simplify this. We get 1 over 6 plus 2, so 7 over 6. No, 13 over 12. 13 over 6, sorry. Now this is 1 over 6. This is 2. Yep, that's correct. And this one is 26 over 24. So we get 26 over 12. Here we get 2, so that's 12, 24, 25. Might be discriminate. So it's 2, so that means 24 over 12. Plus, yeah, that's 25. This case is we have 2 over 12 and 24 over 12. Right? Okay, makes sense. So we got 26 over 12 and 25 over 12. So if we now plug it in into our moment of inertia, into our equation, squared. So give a moment. 25 megapascal kilonewton meter. It doesn't matter actually, because you can x times a over 26 over 12 a cubed t, and for the moment of inertia or for the stresses and the I-beam, we get same moment applied, so same mx, same y, say, and then we get 25 over a cubed t. So you can immediately draw a conclusion actually from this equation already. Well, actually, you could already draw the conclusion from this step. Because the moment applied and the y distance is the same, what yields the best solution is what gives you the lowest stress in this case. So the moment of inertia of the square is larger than the moment of inertia of your I-beam. So the square will automatically means gives you lower stress. So in this case, you could say that your square is the best. So now comes it in. So what best means, right? So there's one part of the solution is basically identifying that the moment of inertia is large for the square, so that therefore give you lowest stresses. But at the same time, the question basically asks you, since you have at disposal an aluminum sheet of 5 millimeter thickness, so you can basically go one step further. It's not implied in the question, so this is basically sufficient to answer the question. But if, say, the question was, which gives you the most optimal use of your material, then this is not the end solution of your question. Because now if you look at it, now you have to basically make a comparison between how much material is used. So for the square, how much material you use? You have basically four sides that are all equal AT. So you have 4 AT, that's your total area. And for I-beam, you have equal to 3 AT. So from a weight perspective, you can make a trade-off for the given condition. So stresses you can determine, because this is known, moment of inertia is known, your moment of inertia is known, moment of inertia is known, moments are given, and your maximum stress is also given. So you can plug in for both cases, you can solve for A, for the square, and get an A value, say A squared here. And you can do the same thing, and then you can get an AI value. Say, let's assume numbers. I haven't gotten the numbers, but what you realize, say you get, say, 2.5, and here, in order to meet the same area, your thickness has to be slightly larger in order to get the same stresses out of it. Say it's 3, right? If you now plug in the A for the two where we solved for the same stress, if you plug it into your area, you will get here 4 times 2, 2.5, so you get 10T, and here you get 9T. So even though you require a larger thickness or larger A value, so your structure has to be larger in order to cope with the stresses. If you look from a materials perspective, your I-beam is better in handling the stresses. So here comes in the fact, where do you stop? Go to the slides. Yeah. So here comes in to understand what's meant with best. And in this case, the solution or the question is not specific, so you can stop at either point. So it's you as an engineer to interpret which is the best solution, saying by calculating the moment of inertia and saying your moment of inertia for your square is larger, therefore your stresses are lower. isn't sufficient way to stop, and justify it's a good justification for why you choose your structure. And the second step, if the question was which cross section is most efficient in material use or most efficient, then you have to go one step further and determine the A values for both the square and the I-beam, and you get two different A values. But because of here you have basically a factor of 25% more material needed for the square than for the I-beam. The I-beam can be a better solution in this case. And two of the three problems will require you to go that extra step. In the take-home exam, it's pretty well defined that you have to go to the step, so you don't have to think it of yourself. So, but you have to go that step. So you have to look at, say, for example, yes, I determined the structure, but is it also the best in weight, in cost, and material usage? Okay. Are there any questions? I know we went through this. I didn't go through the derivations, but what you have to do is, again, this was a homework assignment, so not an in-class problem, or not an exam problem. So the correct procedure would give you, you can just come up with the equation, you can program it in, say, MATLAB, Python, or even Excel, and then you can find which A gives you the right numbers. So I recommend you doing this exercise at home as well. Just fill in all the numbers. I'll post the solution online, and you can see if you did it correctly. Okay. So we have 10 minutes left. I'm going to leave it at that for this lecture. And next lecture, we just go through the book. I'll pick up some problems that's just good to do. Are there any questions? Nope. One more thing. If you have any questions regarding the exam, I will be available online. So just email me if something is unclear. I think everything is pretty clear. And I'll get to you guys soon. Basically through announcements or through direct email. If I think the question is valid for everyone, I'll make an announcement. And if it's just something similar, very small, then I will just reply to you per email. Okay. Thank you.